Okay, I want to do example 303 and 304 here. Both of these are very similar to the ones we just did. We're trying to determine if a set of vectors is linearly independent or linearly dependent. So we're going to set this up just as before, only now instead of vectors from R3 or R2, we've got vectors from M22 and from the polynomial family. So let's do this. All that you really have to do on these, you treat them exactly the same, except for you have to come up with a order in which to convert these into vectors. I'm going to use this as my order. On each one of these, I'm going to go in that direction. I'm not going to write this out completely. I'm going to be a little bit lazy. Because what I'm going to do is I'm going to set C1 times this guy plus C2 times this guy plus C3 times this guy plus C4 times this guy, and set all that as equal to the 0 vector, which in this case is that. So I'm going to jump straight to writing this as an augmented matrix. And so this first one, for my C1 column, I'm going to get -2, -1, -1, 1. I'm going to move this up a little bit. So I get that. Then for my C2 column, I get -2, 3, 2, 1, -1, -3, 0, -2, 4, then 4, 0, 1, -2, like this. And then I just have to row reduce this. So let's put it in. All right, does that look right? I always double check these before I do them, before I row reduce them. And it looks like I entered it correctly. All right, so what do we get here? Is that the whole thing? 1, 2, 3, 4. Yeah. All right, so we have to look at this and say, with this this matrix that we got, I'm not going to copy it. I'm just going to look at it on the Octave screen. If you look at this, we've got a free variable here. Free variable, let's see, C1, C2, C3, C4. It looks like C4 is a free variable. So what that means is we can pick any value we want for C4 and get a solution. So this thing has infinitely many solutions, not just the trivial one. So free variable C4, that means infinitely many solutions. And that means that it is linearly dependent. All right. Let's look at this next problem. Determine whether this set of vectors from P2 is linearly independent or linearly dependent. So I'm going to write this one out, and then we'll convert it to a matrix. So what we have to say here is C1 times x squared plus x plus 1 plus C2 times 3x plus 4 plus C3 times x squared plus 2 equals the 0 vector. What is the 0 vector for polynomials? Well, it's just the number 0. You can think of it as being 0x squared plus 0x plus 0, but just write it as 0. All right. So let's see, how can we write this as a matrix? Well, basically, you're going to treat this as the vector 1, 1, 1. This as the vector 0, 3, 4. and this as the vector 1, 0, 2. Just looking at the coefficient of x squared, x, and the constant on each one of those. So when I write this as a augmented matrix, the C1 column is going to have 1, 1, 1. The C2 column is going to be 0, 3, 4. And the C3 column is 1, 0, 2. And then over here, my 0 vector is 3 zeros. You might look at this and say, well, this is P2, but then I'm converting it into something from R3. So yeah, P2 and R3 are essentially the same. It's just one of them we're treating as a point in three-dimensional space. The other one we're treating as a polynomial. But functionally, they're exactly the same. So let's take this and row reduce it. 1010 1300 1420. All right. Notice what we get out of that. We get the identity matrix. And so all we get out of this is the trivial solution. So C1 is 0, C2 is 0, C3 is 0. We get only the trivial solution. Therefore, these are linearly independent. I guess the most important part there is the end part, linearly independent. All right, one other thing I want to mention before I end this video is this fact here. It says if you've got a collection of k vectors from the subset, if you've got a subset of k vectors from Rn, if n is bigger than k, that's backward. I'm going to fix this in your notes. If k is bigger than n, then S is linearly dependent. So what that means is, suppose you have three vectors from R2. They are going to be linearly dependent. Now, the reason for that is, you start picking vectors out of R2, you pick your first vector, and it's fine. You pick your second vector, well, if it lies on the same line, then they're linearly dependent. If it doesn't, so, I mean, it is possible to pick a second vector so that they're linearly independent. But when you pick a third vector, it's got to be a linear combination of those two guys because they already span the set. So if you've got three vectors in R2, they have to be linearly dependent. And you could say the same thing about four vectors in R3. Linearly dependent. All right, so we'll stop that here.